Gluons behave as if they were a quark-antiquark pair. So you can have, for example, a red quark and a blue antiquark. We usually designate an antiquark by putting a bar above the colour name. Once again, we adopt the principle that anything that can happen does happen. So let's consider how a red quark might convert to a green quark. Here is the red quark in our Feynman diagram coming in and going out. And here is a pair production of a green and anti-green quark. What does this actually mean? It means that a red quark has come in, a green quark has gone out, and a red-green bar gluon has been produced. So in this case, a red quark has converted to a green quark by the emission of a red-green bar gluon. But we can do it the other way round. We can have a gluon assisting the change of colour in a quark. Here we have a blue quark coming in and going out. Here we have a red bar annihilation. A red quark comes in, a red bar quark comes in, and the two annihilate. What is this actually showing? It's showing a blue-red bar gluon coming in, and a red quark coming in, and a blue quark going out. So in this case, a red quark is converted to a blue quark by an incoming blue-red bar gluon. This means that quarks can change colour either by the absorption of a gluon or by the emission of a gluon. But it goes further. Gluons can also make gluons. Let's consider the situation where a red blue bar gluon comes in. The blue bar continues here, the red continues here, and we have a green bar creation. What this is saying is that a red blue bar gluon comes in, but two gluons go out, a green blue bar and a red green bar. One gluon has produced two gluons. In this respect, gluons are different from photons. The virtual photons which work in the quantum electrodynamics model can't produce anything else. But gluons, they can make other gluons. But otherwise, it's the same principle. Just as photons are the exchange particles or gauge bosons which govern the electrostatic or electromagnetic force, so gluons are the force carriers or gauge bosons which govern the strong nuclear force, and that's called quantum chromodynamics. Gluons hold the quarks together. They essentially glue them together. That's why they're called gluons. But there's a difference between quarks and other charged particles. If you have two, say, electrons, the further apart they are, the weaker the force, because this is governed by the Coulomb law, where the force is equal to the product of the charges divided by a constant times the distance squared. So the further away you are, the lower the force. But when it comes to quarks, the force between two quarks is independent of the distance. The more you pull them apart, the force remains the same. So you would need an infinite amount of energy to separate two quarks. That is what is called quark confinement, and it is the reason why you cannot produce an isolated quark. They can never leave the proton or the neutron because they are confined within it. You would need an infinite amount of energy to get a quark out. In practice, what happens if you try to do this is that a quark that you might think could be removed from a proton or a neutron will get to a point where energetically it's easier for a pair production to occur. So in this case, we have a situation where we think that the blue quark is just about to leave the proton. But in fact what happens is that the amount of energy will simply create a blue bar pair production. Then this blue goes back into the proton and leaves the proton, and the blue bar joins the other blue quark to produce what's called a meson. A meson is always a quark-antiquark pair. Mesons don't last very long, they quickly decay into electrons and neutrinos. So it is gluons which hold the quarks together and is the reason why you can never ever have an isolated quark. That's called quark confinement. And that is the essence of the strong nuclear force. But gluons also hold protons and neutrons together within a nucleus. Sometimes that's called the residual nuclear force. This type of nuclear force, however, is not like the quark-quark force, which is infinite. Here, the force between the nucleons, the protons and the neutrons, extends only for the width of the nucleus. The shape of the force looks something like this. But a precise description of what that force looks like is the subject of nuclear structure physics, and I covered that in one of my previous videos. How then do the gluons help the protons and the neutrons to stay in the nucleus? This is achieved by what is called pion exchange. Pions are mesons. And here is an animation which demonstrates what is going on. First, I need to acknowledge that this comes from Wikipedia. It's part of the Wikipedia Commons arrangement, and I gratefully acknowledge Wikipedia and the producer of this graphic. Let's slow it down and stop it to see what is actually happening. First, we have a proton and a neutron within the nucleus. Gluons are being absorbed and emitted, as we have already seen, and in the process they are changing the quarks from one colour to another. In due course there is enough energy for a pair production, and this leads to the creation of a meson, as we have seen. In this case it is a pi meson, or pion. The pion then travels from the proton to the neutron, where it is absorbed and produces more gluons which interact with the quarks to change their colour. This will lead to the production of a further pion, which travels back to the other particle, and the process starts all over again. That process of pion exchange produces the force that holds the nucleons together. So to summarise what we have covered in this video, firstly we have learnt a little more about what constitutes the electromagnetic force. The quantum electrodynamics explanation says that there is a gauge boson, the photon, which as it were mediates the exchange of information between the two particles. Secondly, we looked at the weak interaction, and in particular when protons convert to neutrons or neutrons to protons. We see that they do so by the emission of a W plus or a W minus boson, and that is the gauge boson that mediates that weak interaction exchange. Thirdly, we looked at the strong interaction, which is the process which holds quarks in protons and neutrons, and that's called quantum chromodynamics, and is the means by which gluons change the colour of quarks. And it is also the source of the residual strong nuclear force, which is the means by which the nucleons are held together in the nucleus by pion exchange.